Right now, your computer has absolutely no idea what the letter A actually is.
Oh, definitely not.
It doesn't know what a 1 is or a 0. I mean, behind all the glowing pixels on your screen, every single piece of human language is basically just a number wearing a mask.
Right, a numerical value in disguise.
Exactly. And the moment we forget that, we start writing code that forces machines to think like humans. And that usually ends up being, well, a massive performance bottleneck.
Oh, completely. It's a huge drag on the system.
So welcome to today's deep dive. Today we are tearing apart a really fascinating developer journal entry. It's titled Notes on Haskell-Programming, Part 176.
Catchy title, I know.
Right, but it was published on July 2, 2026 by a developer named Ang. And on the surface, it looks like a simple breakdown of an update to a console app, one that just converts standard Chinese text into numerical digits.
Yeah, but the real mission of this deep dive is exploring something much bigger. It's that eternal tension between code that makes sense to a human reading it and code that makes sense to the silicon actually executing it.
The tug of war.
Exactly. Ang took this perfectly readable piece of code and just dismantled it, stripped away all the natural, descriptive human logic, and replaced it with the hidden mathematical architecture of the alphabet itself.
Okay, let's unpack this,
Yep.
because we have to look at the starting line first.
Yep.
The original code base had this function, and it was named to fullwidth char.
Right.
And the whole objective was just to take a standard ASCII digit, like a 0 through 9, straight off your keyboard and map it to its full-width equivalent.
And for those who might not know, full-width characters are those wider versions of letters and numbers that you see used heavily in East Asian typography.
Yeah, so they can align perfectly within the square grids of written Chinese or Japanese characters, right?
Exactly. I mean, a standard one is physically narrow on the screen, but a full width occupies the exact same horizontal real estate as a dense, complex Chinese character.
So they had to convert them. And the way the original code achieved this was by utilizing a literal pattern matching block. It was just a case-by-case list in the code.
Very literal.
Yeah, if the input is 0, output the full width. If it's 1, output then. It just stepped through all 10 digits. And then it finished with a catch-all rule, an underscore pointing to a variable, instructing the program to just pass any non-matching character through completely unchanged.
Right. Which honestly is a direct translation of how we think as humans.
Oh, totally. If you hand someone a sheet of paper and ask them to swap out specific symbols, they mentally create a checklist.
Exactly.
To picture how this executes, just imagine a bouncer at the door of an exclusive club, and this bouncer is holding a literal piece of paper with exactly 10 VIP names on it.
I love this analogy.
Every time a person walks up, the bouncer stops them, takes their ID, and checks it against the top name. Are you 0?
Nope.
Looks down at the list. Are you 1? Nope.
Right. They have to verify every single line item sequentially until a match is confirmed. Or they just exhaust the whole list and send the person to general admission.
Right. And to a developer who comes in and reviews that code base months later, the intent is immediately transparent. You can see the exact mapping. The friction only really occurs when you try to scale the operation.
Because checking a list, item by item, is an ON operation. Even if n is small, like 10 items here.
Yeah, if 10,000 characters suddenly hit that function, your bouncer becomes a massive bottleneck.
And at the hardware level, pattern matching is essentially a series of conditional branches.
Like little forks in the road for the CPU.
Exactly. And a modern CPU relies heavily on something called branch prediction to keep its instruction pipeline full. It tries to guess which way the if-else logic will go before it even evaluates the condition.
So it's trying to predict the future to save time.
Right. But when you feed it a random stream of text and run those characters through a 10-step checklist, the CPU is going to frequently mispredict the branch.
Oh, I see.
And when it guesses wrong, it has to completely flush its pipeline and start over. That wastes precious clock cycles. The computer isn't just taking a little longer to read the list, it's actively stumbling over our human-readable logic.
Which means the bouncer needed to be fired entirely.
Completely let go.
We needed a mechanism to let the VIPs in without checking a list at all.
And that requires shifting our whole perspective on what characters fundamentally are. When a system renders a full-width Chinese digit on your screen, it isn't rendering a shape based on an image file. It's rendering a Unicode code point.
Which is just a number.
Yes. Unicode is the universal standard that assigns a unique numerical value to nearly every character across global languages. And the critical detail Ang leveraged here is that these specific Unicode blocks are perfectly contiguous.
They sit right next to each other on the number line.
Exactly. The system doesn't just know 0, 1, and 2 exist. It inherently understands they are mathematical neighbors living in sequential memory spaces.
Okay, so let's get into the specifics. Where do they actually live?
So the standard ASCII character for zerogon sits at the hexadecimal value of 0x00000.
Okay.
And Ang looked at where the fullwidth resided in the Unicode spec. It lives much further down the hex chart at 0xF10.
Right.
And because both the standard ASCII digits and the full-width digits were mapped in perfectly sequential blocks, this incredible optimization opportunity suddenly appeared.
Right, because you don't need to ask the bouncer 10 different questions. You just measure the distance between the two blocks.
You calculate a mathematical offset. Ang realized the physical distance between standard digits and full-width digits is exactly 0x feet.
Wow.
So if you take the standard 0x00A3 and simply add 0x feet, you land precisely on 0xFF10, the full width.
And it just maps perfectly for 1, 2, and the rest of the block.
What's fascinating here is how this completely redefines the workload for the processor. We transformed a search and compare operation, which had multiple conditional branches, into a single, flat addition problem.
No guessing required.
Exactly. By leaning into the sequential nature of Unicode, the need for case matching just evaporates. Branchless programming is incredibly fast because the CPU never has to guess which path the logic will take.
There's only one path.
Right. The instruction pipeline flows without interruption. It is just raw, deterministic math.
Now, here's where it gets really interesting. And honestly, this is where I have to step in with some pushback.
Over.
Because I'm looking at this from the standpoint of the next developer who has to maintain this repository. The original pattern match listing 0 through 9 was totally self-documenting. It visually explained its own purpose.
It did, yeah.
But Ang's new implementation replaces all that with full width offset equals 0x feet. I mean, without heavily commenting the code, that looks like a magic number dropped out of the sky.
It does look pretty opaque.
It reads like a secret cipher. So we are saving microscopic fractions of a millisecond by removing those CPU branches. But are we sacrificing the maintainability of the code base to do it?
Well, it is the eternal developer's dilemma.
Yeah.
Right? You are absolutely trading immediate visual comprehension for structural elegance.
Yeah.
I mean, if a maintainer doesn't have a Unicode hex chart memorized, which nobody does, they're going to have to stop and research why 0x feet is there.
Right. It stops them in their tracks.
But for an application processing potentially millions of characters, those microscopic fractions of a millisecond compound, they turn into massive latency reductions at scale.
So human logic is highly descriptive, while machine logic is purely structural.
Exactly. When a script only runs a small batch process once a night, sure, a readable pattern match is usually the right choice.
It's fine.
But Ang's application is a console tool designed for speed. You reach a performance threshold where you literally have to stop speaking human language to the computer and start speaking its native dialect.
Even if it looks like math.
Right. The code becomes abstract, but it aligns perfectly with the underlying physics of the machine.
Okay, but the hex offset was actually only solving half of the problem, wasn't it?
Yeah.
Because firing the bouncer and replacing him with a mathematical fast pass is great, but if the club's entry hallway is like a mile long and filled with hurdles, you still have a bottleneck.
A huge one.
Which brings us to Ang's second major realization. And this one tackles the hidden tax of data conversion.
Right, the overhead problem. Because the original implementation wasn't actually operating on a solid block of text. To process the string, the program was constantly converting the text data type down into a list of characters.
Which seems redundant.
It is.
Yeah.
In Haskell, that translates to moving from a highly optimized text structure into a standard string, which is fundamentally just a linked list of char elements.
It dismantled the entity just to inspect the individual part.
Exactly.
To visualize the overhead here, imagine a commercial shipping operation.
Got it.
They receive this beautifully packed, perfectly sealed, highly secure shipping container. This container represents our text data type. It is optimized, it's contiguous, and it's ready for rapid transport.
Because the data inside a text type is stored sequentially in memory.
Yeah.
It's all together.
Right. But the old logic requires the shipping company to put a tiny sticker on a few specific items inside. And instead of finding a way to tag them in place, they tear the whole container apart.
Just rip it open.
Yeah, they pull every single individual item out and lay them down in a massive sprawling line across the entire warehouse floor. This sprawling line is our char list.
And this is where the hardware realities hit hard.
Right.
Because a char list in Haskell is a linked list.
Right.
When you lay those items out on the warehouse floor, they aren't actually next to each other physically. In computer memory, each character in a linked list is allocated dynamically on the heap.
They're scattered everywhere.
Exactly. Character 1 might be in memory block A, but it has to hold a pointer directing the system way over to memory block Z just to find character 2.
Oh, wow.
And then character 2 holds a pointer to block M for character 3.
So the CPU literally has to run all over the warehouse just to read the next item.
It's called pointer chasing.
Hmm.
The CPU cache, which is the ultra-fast memory right on the processor, is designed to pull in contiguous blocks of data.
Right, things that are next to each other.
But when data is scattered across the heap in a linked list, the CPU constantly suffers cache misses. It has to fetch data from the main RAM instead, which is magnitude slower.
So our shipping company is running back and forth across the warehouse for every single item.
Yep.
They check for the ones that need stickers, they apply that 0x feet offset, and then they aren't even done. They have to construct a brand new shipping container and repack thousands of items before the shipment can finally move on.
And the waste in physical cardboard, tape, and labor in that analogy is enormous.
Huge.
In software, that waste translates to massive CPU cycles lost to pointer chasing, plus the memory allocation for all those list nodes, and the eventual garbage collection required to clean up that scattered list once the new text object is finally built.
It's just a massive tax. But
Right.
ANG's solution bypasses this entirely, right? With a new function named to full-width text.
Right.
Instead of breaking the string apart into a linked list, ANG utilized a function provided by the data text library. It's called tl.map.
Right. TLMAP allows the application of our bitwise offset function directly over the internal structure of the text type.
Without breaking it apart.
Exactly. Without ever converting it to a list of individual characters first.
So going back to the warehouse, it's the equivalent of the shipping company utilizing a specialized magnetic scanner.
Oh, I like that.
They just wave the scanner over the intact sealed container. The scanner interacts with the specific items inside, applies the changes magnetically, and the container never has to be cracked open.
It stays fully packed.
Stays fully packed and just keeps rolling down the logistics line.
If we connect this to the bigger picture, we are looking at the severe hidden tax of data translation. Moving data from a high-performance type like text, degrading it into a linked list of characters for inspection, and then forcing it back into text. It creates unseen overhead that taxes every single operation the system performs.
It's doing so much busy work.
Exactly.
Yeah.
By mapping directly over the native structure, ANG preserves memory locality. The CPU can pull that contiguous byte array straight into its L1 cache. It applies the offset sequentially without jumping around the heap and writes it back out.
Oh.
No node allocation, no pointer chasing, and drastically reduced garbage collection.
So we have two massive structural improvements here. The pattern matching list is replaced by a pure mathematical offset, and the data conversion tax is eliminated by mapping directly over contiguous memory.
Which culminates in ANG's updated master function, Chinese numtoint.
Right. And this final architecture demonstrates how to deploy these highly optimized, low-level tools within a broader, stable system.
How does it work together?
Well, the refactored Chinese numtoint function basically acts as an intelligent traffic director. When a string enters, the function performs a rapid, elegant evaluation using tl.all is digit txt. It's basically asking a very simple question. Does this entire text block consist solely of standard digits? And if the answer is yes, it routes the data straight to the fast lane. It directly applies the new to full-width text mathematical offset, and the operation finishes almost instantly.
But it also accounts for the messy reality of real-world data, right?
Right.
Because if the text isn't a clean string of ASCII numbers, say, if it contains complex Chinese characters that actually require semantic evaluation, it bypasses the fast lane. It gracefully falls back or degrades to a heavier, full parsing function.
It reserves the heavy machinery for the edge cases.
Exactly, and lets the baseline data just fly through the optimized math pathway.
So what does this all mean? I mean, we've gone deep into Haskell library functions, branchless CPU operations, and the memory layout of linked lists versus contiguous arrays.
We got pretty deep in the weeds there.
Yeah, if you are sitting there listening and you don't write software for a living, you might wonder why a niche code refactoring from a 2026 dev journal holds any relevance for you.
Well, this raises an important question, because at its core, this isn't just a lesson about Haskell or compiler optimization.
Hmm.
It is a masterclass in systems thinking.
Totally.
Eng's approach is a blueprint for solving operational scaling problems in almost any domain.
Because we all build systems, right?
Yeah.
Whether that's managing a corporate supply chain, structuring a team's workflow, or, even just processing an overwhelming email inbox.
Exactly.
And our default human instinct is always to manage by exception. We create endless lists of conditional rules. If this client emails, route it to Sarah. If that vendor calls, route it to David.
We constantly construct bouncers with VIP lists.
Yes.
And when a system is small, that descriptive, exception-based management all works perfectly. It is highly readable to anyone stepping into the role. But the moment you experience exponential scale, micromanaging individual exceptions just collapses under its own weight.
The overhead kills you.
Right. The administrative overhead of checking the list becomes greater than the actual work being done.
And Eng's refactoring proves that to survive at scale, you have to discover the foundational rules of the environment you are operating within.
You have to look for the structural realities, like an offset that can be applied universally, rather than managing 1,000 individual variations.
It's profound, really.
And beyond that, the data conversion tax applies to human workflows just as much as it does to CPU cycles. You have to ask yourself, are you constantly tearing apart your organizational shipping containers?
Think about how often we export data from one software tool, convert it into a massive spreadsheet, manually adjust a few rows, and then import it all back into another database.
All the time.
We are breaking our data down into a scattered list, processing it inefficiently, and repacking it, instead of finding a way to map our changes directly where the information already natively lives.
Relying on deep structural rules will invariably scale better than hard-coding responses to surface-level symptoms.
You stop fighting the system's architecture and start leveraging its physics.
Exactly.
Well, let's do a quick recap of the ground we covered. We began with Eng's Haskell application, analyzing a code snippet that was highly intuitive for human eyes, but created unseen friction for the processor.
Right, the bouncer at the club.
Yep. Then we explored how abandoning human pattern matching in favor of the contiguous nature of Unicode utilizing that branchless hexadecimal offset of 0xphi resulted in blistering execution speeds.
The math fast pass.
And from there, we diagnosed the hidden tax of data translation, unpacking why turning contiguous memory blocks into scattered linked lists just crushes hardware performance, and how mapping over the original structure solved it.
We essentially traced the journey from human description to pure machine execution.
We did. Now, before we sign off, I want to leave you with a final thought to mull over, something that stretches this concept of offsets and hidden mathematics into the communication we rely on every single day.
Consider the fact that every letter, every emoji, every sentence you read on a screen is just a numerical value draped in typography.
Just a number wearing a mask.
Right. When you draft an email or send a text, the glowing pixels are an illusion. Beneath them, it is all contiguous, sequential math. If our entire digital vocabulary is just mathematics waiting to be executed, how much of our daily digital interaction could be radically reimagined if we stopped staring at the literal words and started manipulating the numerical offsets hiding underneath?
Wow. It completely shifts how you view a screen, doesn't it? Well, the next time you are bogged down by an inefficient process, we encourage you to look closely at your own architecture. See if you can fire the bouncer, stop unpacking the shipping containers, and find the hidden offsets in your own systems. Thank you for joining us on this deep dive. Until next time.